Hello, my name is Kaya Brown. This is Lab 4. It's on circuits. It's for Physics 2212. So the introduction of this lab, essentially we're going to learn about these basic circuits with these pretty typical components, which include capacitors, resistors, batteries, light bulbs, things such as that. And then we're also going to focus on some basic circuits concepts and fundamental equations. And then we're also going to observe the behavior of these electronic components. So to introduce some of our fundamental concepts, we have the node rule, the current in equals the current out. We also have the loop rule, which means calculating the potential difference, it should equal 0 at the end. And then we have Ohm's law, which means the change in voltage equals the current times the resistance. So our assumptions, surroundings, and systems. So an assumption here is that the resistance of the wires and ammeter are negligible. In real life, they would factor in somewhat to our calculations, but for this model, they don't. And then we also have our system, which is a circuit, and then our surroundings, everything else. So the procedure of this lab, we have our simple circuit right here. We have 2 ammeters. We also have 2 batteries that are 1.5 volts each. And then we have our 2 resistors. So we did our little Ohm's law calculation to predict the current before reading the value of the ammeter. And we got 0.02 amps. And then we ran the experiment and we got the same value. We also reversed one of the ammeters, and we discovered that the value becomes negative. It reads the current in an opposite direction. And then we also connected a voltmeter, and the voltmeter calculated the total volt, which is 3, which is the calculation of both batteries. So this is also calculating the potential difference. So on different sections of the circuit, we calculated the potential difference here. And as you can see, it varies a little bit, and then we ended up getting the total voltage, the potential difference equals 0, which follows the loop rule. Pretty cool stuff. So we also calculate the potential difference. So that's that. And we also have a graph that details the potential difference and how it changes, just to have a good visual of how that works. And as you can see, it does have places where it plateaus, increases, decreases, but at the end it finally equals 0, showing that the potential difference does go to 0. So we have our calculations here of the just calculating the different resistances. So we have a resistance obviously of the 2 resistors, which is already given, and then we calculated the resistance of the wire and the ammeter, which are 0, which is based on our previous assumptions. So we also have another circuit where we connected instead a light bulb, a capacitor, and a battery. So after the light connected, it progressively dims over time. This is when you charge the capacitor and then disconnect the battery. And then when the battery is disconnected, the light dims over time. It doesn't dim automatically. So the current in the capacitor, it decreases until it reaches 0. So we also calculated the times for the capacitor to charge. So for the 10 ohm, it's 8 seconds, and then 20 ohm, it's 20 seconds, and then for the 10 ohm, for the capacitor to discharge, it's similarly 11 seconds, and then for it to discharge for the 20 ohm bulb, it's 21 seconds. So then we created another circuit. So this circuit is pretty similar in components. It's our RC circuit, and then we charged this capacitor and then got rid of the battery just to see the voltage difference over time. So this is what the chart shows right here. So after that, we have essentially our graph here, and our graph is using this formula that we have in the lab procedures, which is Ln over the potential difference divided by the initial voltage, which is 9. So we have those plotted, and it's this little linear graph right here. And then we use the slope of that graph to go ahead and calculate RC, which is 5.92, which is very close to our expected value of 6 seconds. So we have our discussion question. So we see that if we use an actual ammeter, we would essentially get a good bit of resistance, but since this is a digital model, it does not factor into the ammeter, so there's no resistance. And then if we were doing this lab in real life and used a real battery to charge the capacitor with no resistor, so how quickly would our ideal model predict the capacitor reach full charge? Would this prediction happen in real life? So essentially there'd be a latency in charging of the capacitor, and this would be just due to like general resistance. So there would just generally just be like a little bit more waiting time with the entire experiment. So this is the end of the presentation. Thank you for watching.